horizontally by a factor of 2, that tells me that my b value is 1 over 2, right? There's no negative, so I don't have a negative. Stretch horizontally by a factor of 5, b equals 1 over 5, right? It's the same thing over and over. Here, stretch horizontally by a factor of 5 over 3, so b equals 3/5. Okay? Now it didn't ask you that. It says what should be done to y equals x squared to stretch or by each of the following. Stretch horizontally by a factor of 2. Sorry, how do they want the answers again? Screw things up here. Yeah, so I kind of answered it differently. They said replace x by half x. That's just another way of saying b equals a half, right? b equals 5/8. All right, so same thing. What should be done to shrink the graph horizontally by each of the following? Shrink horizontally, so then b equals 3, right? They don't have a negative here, but if the negative sign stays, like if it said shrink horizontally by a factor of -3/5, if they put the reflection in as well, the negative sign stays. We talked about this one already. If the original graph is y equals x squared plus 7, I would accept this. I think this is a better answer. I would say it's a vertical compression by a factor of 1 over 4. How many people see that? Would agree with that? How many people would answer that? That's how I would answer on a test. They made it more difficult, and I'm not sure why, just testing your algebra skills. They called it, or a horizontal stretch by a factor of 2, right? If it's going to be vertical compression, if it's compressed vertically, it would expand horizontally. So what happened was the b value, actually it's hidden in here because there's no brackets, the brackets have disappeared, and b values always start out with a set of brackets. So the b value must have been 1 over 2. Okay, so b's are always included inside the brackets. Because 1 over 2 squared is the only way that would leave you to a simplified 1/4, right? So to figure out the b value, just square root the coefficient. That's all you're going to do, right? But to me, this is a better answer. And on a test, this is what I would expect most of you to, if you want to be fancy, you could call it horizontal. And again, that only happens for certain graphs. It only happens for parabolas or absolute values. So same thing happened here. And then we had another, I think we talked about this already, didn't we? Yeah, sorry, I'm repeating myself. We talked about that. Okay, the next thing I got you to work on was, I gave you a little hand-in assignment, or not a hand-in, check assignment. So it looked like this, check your understanding. Were there any questions at all on this? I was scrambling yesterday, if you remember, because all of our systems were down in the school all day. So we didn't have any printing capabilities, and actually even Microsoft Word crashed yesterday. Yeah, on that paper. Okay, let's take a look at question 7. And then we're going to try and finish off the unit stuff today. We're trying to finish off reflections and inverses. Okay, so let's take a look at number 7. I'll get a clean copy. Okay, so let's see. So 7 has 2 parts, and this is the perfect type of question that you'll see Wednesday. You're given some instructions, a description. You have to turn that description into an equation, and then we have to graph that. So the graph of f of x is 1 over x is stretched horizontally. We haven't worked a lot with this equation, have we, Jack? We've worked a lot with x squareds and with absolute values. This is the reciprocal graph, right? So here's my graph. Do you remember what this guy looks like? This is one of your kind of parent functions that you've been exposed to that you kind of have to have a bit of an idea. Do you remember what that one looks like? No? Some people describe it like a pair of wings, right? So it's the one that looks like this. Agreed? So that's what one of ours looks like. And the two identifying points, I would say, are 1, 1, that's a critical point, -1, -1 is a critical point. Does this guy have the asymptotes? Lines where the graph kind of grows towards but never touches? Both of the axes are asymptotic. So I've got y equals 0 is the, and this is just my shorthand for the horizontal asymptote. And then this one, I've got x equals 0 is the vertical asymptote. Okay. We'll explore this graph in much more detail when we study rational functions, but this graph actually started as y equals x, and it is transformed when you put x on the bottom, because, and that makes these two guys asymptotes, because x can never equal to 0. You can't divide by 0. That's why there's an asymptote there. Okay, so if you know what the graph, that's again why I stressed knowing your parent functions. If you know what the graph is supposed to look like, that helps you a lot when you're reproducing the graph, right? So that's kind of where I'm starting from, right? Okay, so now it says graph the function. Okay, so what are the changes we have? Again, I'm going to list the changes in words. Stretched horizontally by a factor of 4. What does this statement mean? What value does this give me? My A, my B, my H, or my K? Yeah, so B will be 1 over 4, correct, Johannes? Reflected in the x-axis. That means, yeah, that's a minus on the outside the whole graph, right? So A equals negative. I guess a -1 we'll say. If there's a reflection, it's a -1. There's no other stretch. Translated 4 units to the right. So then I would say H equals positive K. And 1 unit down. K equals -1. I'm kind of using different variables, but I'm using these guys, right? A, F, B, X minus H plus K. So A is my -1, B is 1/4. The 4 goes right in here, right? It goes in as positive, so it becomes X minus 4 and then minus K. Okay. So determine the equation of the function g of x, okay? So g of x will be equal to, okay, so I have my 1 over x, right? That was my original graph. The negative sign goes outside here, right? That's where my a value goes. So I've done that one. This goes, where does the b get attached? What variable does b get attached to all the time? B goes right, it's a coefficient on x, right? Okay, so I've done that one. K is easy. K is always just outside the function. A and K are outside the function. Okay, this has to show a shift 4 to the right. So anytime I have a B and an H, I'm going to have brackets around the X. Okay, so that's the equation. Yeah? Okay, so follow the same rules. Now we have to graph.
You didn't use F, just you can use.
I didn't have to use F because they didn't give me F in the original, right? All right, so now what do? If I have, there was a vertical shift, I'm gonna 1 down, horizontal shift, 4 to the right, horizontal stretch by 4, that was given to me, right? So the important ones are these guys, right? Anytime there's shifting, remember, any shifting will also shift any asymptotes. So I have 2 asymptotes. So my vertical asymptote will be shifted 4 to the right. So the new asymptote, new vertical asymptote will be x equals positive 4, right? It shifts from 0 to 4. My new horizontal asymptote will be shifted 1 down. So my new horizontal asymptote is y equals -1. All right, so I'm going to take a pen, a red pen, my ruler to make sure I get everything nice and sharp. So here's my new. I'm going to show you a real quick way to graph anything with an asymptote. And again, we'll go into more detail when we actually do this unit, because we're going to be doing transformations on the reciprocal graph. Okay, I'm just going to graph using these 2 critical points. Can you believe it? I'm just going to use 2 critical points for now. I'm doing a quick sketch. And I'm going to use my knowledge of the parent function. I know what it looks like. It's a pair of wings. And I know that it's asymptotes. And asymptotes kind of almost take the place of critical points in a way, because they can really help you. So, my 2 critical points were what? I had 1, 1 and -1, -1. So I'm just going to do a really quick little chart here. And what do I need? I'm going to have, it'll be a 4x plus 4 for my x changes, and then on my y, a -y minus 1, -y minus 1. Okay, I'm going to multiply every x by 4 and add 4. So 4 plus 4, that'll be 8. And this one, -4 plus 4 gives me 0. Okay, and then this one, oops, sorry. Okay, so once again, my changes are multiply every x value by 4 and add 4, because it's a shift right. So 4x plus 4. Take y's and they become their opposite sign, and then subtract 1. So -y minus 1. 4 times 4 plus 4 is 8. -1 times 4 plus 4 is 0. The opposite of 1, -1 minus 1 is -2. This will be a +1 minus 1. This will be a 0. Okay, I might have to do some more information too later on, but we'll see. So I have a point at 0, 0, and I have a point at 8, -2. Okay. That's not much to work with, but if this was just a real quick sketch at this point, I have 1 point, and I know that a graph, what graphs do is they try and grow towards asymptotes. And asymptotes keep them fenced in. They can't cross, they don't, they'll never cross a vertical asymptote. And generally, they don't cross the horizontal. So basically, asymptotes, and you know that it has to look like a pair of wings, right? See what happens from this 1 point? They grow in both directions towards the nearest asymptotes, but they never ever touch the asymptote, right? They just keep getting closer and closer and closer. With that knowledge, can we do this? So I've got this 1 point. The only direction, and it's got to grow in both directions. It's got to grow here, and then it also has to grow here. Agreed? From this 1 point, it's got to grow in both directions, so it grows here and here. And I'll be talking more about how to sketch asymptotes when we have a whole chapter devoted to these types of functions. Now, you could do a couple more point plottings if you wanted, but my instructions are just going to do a sketch at this point, and sketch means not point plotting 100 points, a general idea. Make sense? That's it. So anytime x appears on the bottom of a function, if you have a fraction and x is on the bottom, you're going to have asymptote. Sorry? Oh, this one? Okay, let's try that one too. That's a tricky one. Oh, this one? Sorry, this, I'm not sure. How did I get the -1? Because 1 minus 0 is the original asymptote on 1 over x. if there's an h value, Johannes, it's going to affect the vertical asymptote. If there's a k value, it'll affect the horizontal asymptote. And there was a k value of -1. Yeah. Okay, we good? I feel like I'm boring half of you. No? All right, let's work through the last set of examples, and because they both involve reflections, I have another little, if you want to do a little assessment for me, I have another short little one today. I'm also going to assign you 2 assignments for the book, through in the chapter book, to get ready for Tuesday, and then I'll have more review for you Tuesday. Tuesday's going to be, I figure if I get through reflections and inverses today, then Tuesday is complete review day. No, I'm not lecturing, I'm just going to be here. I will give you another review in class with answers. It's going to be work period, you work through the review, you make sure you know everything, and then you can ask me questions for the test on Wednesday. Because once again, no school on Monday, right? So you have a long weekend. So we'll have some exercises to do in your chapter book today, and then I think you guys are ready. It's a weird little topic, but everyone seems to have, most people anyway who I've talked to seem to have a grasp on it. So let's look at, again, I'm not going to spend a ton of time on reflections. Let's look at page 19 in your examples. And we already know about reflection. About talking in a little more detail in reflections is it leads us nicely into inverses, which are the last lesson in this book, and it's kind of taught you inverses on day 1, and you might have done inverses already, but it's kind of interesting to see why they're tacked on to the last chapter of this book. So let's read this. A function can be reflected in the x-axis, in the y-axis, or the line y equals x. I mentioned that already, right? We've only talked about x and y. The line, this type of reflection is kind of a standalone, and I'm just going to tell you, when a function is reflected in this line, it's called the inverse. Okay, so I'm not going to talk about, in lesson 4, we don't talk about inverses. We're just going to do x and y, because guess what? We have a whole lesson on inverses. That last lesson is just the reflection in y equals x. So we're just going to stick to x and y in this lesson. Note that a reflection in the y-axis, so when things are reflected in the y-axis, the x-coordinate changes sign. When we reflect in the x-coordinate, in the x-axis, the y-coordinate changes signs, and that's about it. That's all you have to remember. Given the graph of this function shown below, sketch the image graph after reflection in the y-axis. State the domain and range of each function. Okay, this is the f of x graph. Is f of x a function? It should be, because we gave it the f name. Does this qualify as a function? Is this picture a function? Joanna says yes, I agree. Why? Passes the vertical line test, right? If I drew a vertical line anywhere, it would be a function. So here we go, sketch the image graph. Do we have to make a table of values, like with critical points, or do you think we could do this one just in our heads, like just free form, freehand? I think we could do it freehand too, okay? So we just have to pay attention. I'm gonna identify 4 points though, like the 4 corners. Do you want to start here, E.B.? You want to start with this point? Okay, so it says reflection in the y-axis. So that means to me, all x values become their opposite. And I'll just put the words in brackets in sign value, their opposite value, okay, the opposite in sign. Okay, so this point, and oh, by the way, no change on the y value. Okay, so if y doesn't change, okay, here was my point. So what are the coordinates of this point? -1, +1, agreed? It just hops over the x-axis to +1, okay? This point just hops over the x-axis. The only thing that changes, its position on the y-axis stays the same, so it just hops over to the negative side. This point here was +5, agreed? So now it becomes -5. And this point was +9, so it becomes -9. And I'm following like a horizontal path across the, because it's just bouncing across the y-axis. It's staying on the same level on the y. Okay, so just remember in this case, it doesn't really matter if I go from left to right or right to left to connect the dots. So is this new graph a function? Okay, because it's a function again, I have a new way to symbolize this, or I'm just going to call, this was f of x, right? So what happened? Reflection in the y value. If I just called this y equals f of x, right? Y equals f of x. This one will be called y equals, the only thing that changed was the x values changed their sign. So minus x. That's it. If this was called f of x, this is called f of minus x. And they wanted the domain and range of each. So domain and range. Just make a little chart here. So we'll do the domain and range of the original and then the reflected. Okay, I think I'm going to do interval notation. The domain of the original was from -1 to +9. And the range of the original was -5 to +3. Now, what do you expect to happen if the x values were just reflected? What do you expect to happen? Will the domain and the range both change? One of them stays the same, right? There was no change on the y's, right? So the y, nothing happened on the y's to the y values, so they're just going to stay -5, +3, as you can see. -5, +3. It's just the domain of the graph changed. So guess what? It happens to be now -9 to +1. Right? The sign's just flipped. So we always write the small number first. That's it. That's all that a reflection does. Generally speaking, though, you're probably not going to get a lot of graphs on the test that are just reflecting. It's usually your reflections come with an A value or your reflections come with an added B value too. But just to kind of dive in. Okay, given the graph, sketch the image of reflection in the X. Okay, it's the same graph, right? We're going to see one thing about reflections, the direction changes, right? Because the whole graph is flipped over, so the directions change. So here, this is going to be a reflection in the x-axis. So all the y values become their opposite sign. No change on the x value this time. Okay, so we'll call this f of x. So same thing, we're just going to pick the points. The x value stays the same, we just reflect over the y. So this becomes a 1, this becomes a +5, and this also becomes a +5, and this value becomes a -3. And I connect my dots again, and I should see the graph pointing in a different direction. And sure enough, it is. So we'll do the same thing. We'll do domain and range. Whoops. Screwed up there. Y equals minus f of x, right? the minus sign goes outside the f. Actually, I'm going to scratch that out. I'm going to do it better. Y equals minus f of x. Because remember, f of x can be also thought of as another name for y. So it's just minus y. That's what that means. Okay, so no change on x values. So the domain stays -9 or -1 to +9. The y values did start off at -5 to 3, right? It was -5 to 3. So now you can, they should just have flipped. It should be -3 to +5, right? Let's see. -3 was the lowest to +5. Literally, that's what you're doing, right? You're changing the signs of the y. So this becomes +5, that becomes -3. All right, we good? Sorry, Evie. Okay, let's take a look. These are a little easier to do because they don't involve, or not easier, but they take less time. They don't involve any graphing. So usually graphing takes a while. What is the equation of the image when the graph of y equals root x plus 5 is reflected in the y-axis? So what kind of change happens with reflection in the y-axis? X values change, right? So all you have to do is add a negative sign to the x value, and that's it. This graph reflected in the y-axis, the whole y value, and this represents, the right-hand side represents the whole y value. Y literally equals this whole expression, the absolute value of x minus 3. So if I want to show reflection in x, a negative sign goes outside the whole value. Is this pretty straightforward for everyone?
Yeah.
Thanks, Spencer. At least I got some response. Okay, what about these? If this is the equation of a polynomial. It has more than one x represented because these are not like terms. I can't do anything about that. I can't combine these any further. So this is simplified form, but the same instructions apply. Write an equation for the image of this function if it's reflected in the x-axis. Okay? So if it's reflected in the x-axis, that means a change in the y value, right? So this whole expression represents y. This is, for every x I put in, this whole set of instruction represents the y value. So you know what we have to do? So, actually I'll call this y equals. So what I have to do is, I have to put a negative sign in front of the whole expression. Okay? This whole thing represents y. So in order to make y negative, I have to put a negative sign in front of the whole expression. So this becomes positive 4x squared minus 3x positive 7. That would be the new equation for the image if it was flipped in the x-axis. Okay, thinking in those terms, what would this, and put it in simplified form for me if you could, what would the expression become if there was a reflection in the y-axis? That means all the x's become their negative values, or their opposite values. How would you represent that initially? What would that look like initially? What's the first step here?
Why are the x values at -1?
Yeah, so every time you see an x, anytime there's a change on x, automatically that means you got to bracket off the x's because there's a change. So my minus 4 just stays there. Every x I see, here's an x here and an x here, it has to be bracketed off, and I have to think of it as opposite of x. Okay, so that's my starting point. Now I step back and I say, okay, can I do any simplifying? Take a moment and simplify that expression. Okay, this is what I got. Anyone agree? Because the two negatives are just going to cancel out and become positive. So that would be minus 4x squared minus 3x minus 7. Okay, let's do this last example and then maybe we'll head into inverses. The function y equals f of x has this domain and this range. Determine the domain and range for each of the following functions, okay? And you could look at example 1b, I think, to help you out with that if you wanted to. So y equals minus f of x or y equals f of minus x. So I want the domain and the range of the function after this change, and I want the domain and the range of the function after this change. Let's see if you could come up with those. Okay, do you agree with my first answer? No change on x values, so domain stays the same. But the y values, if they become their opposite signs, that would give me a positive 9 and a negative 2. Agreed? Always write the negative 2 or the smallest number first. Negative 2 is smaller than 9. When you have reflections, one of your domain or range are going to be, you're going to have to flip the numbers, right? Does anyone agree with this? Thank you. Okay, what about this one? All the x values become their opposite, so then I'm going to have what? This will be a negative 3, negative 12. Agreed? Okay, so this one should, the order will stay the same in a sense, right? Oops, sorry. What am I doing? Negative 12, negative 3, right? Because negative 12 is smaller than negative 3. So when I flip the signs, the order should flip. This one is going to stay the same though. No change on the y values, so the range stays negative 9 to positive 2. Okay, and we've seen somewhat similar things like that. We've done a little bit of domain and range work before. Now you don't know what the function looks like. It doesn't really matter. You can still answer the question even if you don't know what the function looks like, right? They're just asking a concept question there. All right. So are you feel okay with reciprocals or reflections and how to identify them, right? There's going to be a negative on the A or a negative on the B. I think we can proceed. I'm not sure if I'll get through all the examples before I give you guys a break, but I'm going to try. We'll see. And then I'm going to give you most of the second part of the class to do some work and ask me questions. So now let's do this something called inverses. And the only reason they're here, and I think it's a natural place to insert it, is it's just another reflection, except it's on a line that you don't normally use much for graphing, but it's a very important line. This line is called the line where y equals x. So that's the actual equation of the line, y equals x, and it literally means the value for y is whatever x is. So that's the line that contains the 0.11, 2, 3, 3, 4, 4, -1, -1, 0, 0. Every x value equals the y value, or I guess every y value equals the x value, right? So it's a very important line. If you ever get into a type of math in post-secondary, we used to teach a little bit of this in an advanced math class that isn't really taught much before. But it's kind of funny, but you can actually graph, even though this is just a two-dimensional surface, you can actually graph 3D points. Now with computer graphics and that, it's much easier to graph in 3D, but this was called the x value, the y value, and this is sometimes called the z-axis too. If you were going to graph in 3D, because you're graphing horizontally, vertically, and with depth to it. So that's another place you see this y equals x line. It's also the third axis if you're graphing in 3D. But we're going to call this is just the line y equals x. For our purposes, it's we're going to use it for reflections. So because that's an important axis, we know that a point or a function can be reflected over the x-axis, over the y-axis, and now we're going to see it can be reflected over the y equals x line. So it gets literally reflected over this line. It's maybe not quite as easy to see when we actually do a reflection, which is why we're starting off with the graph. You'll see that this, because they're just mirror images, right? When I mirror image over the x or the y, I can also mirror image over here. So the interesting thing is, though, we get to do a little more with inverses because there's a little more to them. So they're a little more interesting. So functions that are reflections of each other in the y equals x line are called inverses. A reflection in the line y equals x results in, and this is really interesting, when we reflect over here, literally all that happens is the x and the y switch places. So the x coordinate switches with the y coordinate. So that's all we do. When we're approaching from an algebra perspective, or even if we made a table of values, if we just used critical points, that's literally all you're doing is just switching the x and y. So it's not really involving any calculation, you're just switching places. So the inverse of a function is denoted by this notation. I'm going to add this, but only if the inverse is actually a function. So when we invert it, we have, if the original function was called f of x, we can call the f to the exponent -1. X is actually called, it's called the inverse, but we can only use that symbol if the inverted graph passes the vertical line test. So we have to be careful about that. If it doesn't pass the vertical line test, it's not a function. We say it's still called the inverse, but it's not a function. We just said this is the inverse, it's just a relationship. Okay, graph the inverse. Now, I think for this one I am going to identify critical points because it's really hard to know how to transfer if you've never done this before. So I'm going to identify some critical points. So this is the original function. And I'm just going to call this the inverse. I don't know if it's a function yet, so I can't use the word function till I know. And you know what we're going to do here? You know how all we do is flip x to y and y to x. So let's identify. What do we have here? We have -2, +6. And then +3, 1, +5, 3. Okay, all I have to do is switch places. 6, negative 2, 1, 3, 3, 5. Plot these. So 6, negative 2, 1, comma 3. And I think I'm going to connect those right away so I don't lose. These can get tricky. So I'm going to, this was my first, this was my second. I'm going to connect those right away so I don't lose my place. And then, oops, and then 3, comma 5. Okay, so I connected 1, 2, 3. Okay, does the red graph, maybe I'll do it in highlight too. Okay, so this was my original graph, right, in black. There's a bit of an overlap, right? Can you see that it's a reflection in that line? This was my black graph. And it's like I took this graph and I just flipped it over. The y, can you see? It's a reflection, right? Now, is the inverse a function? Can you see this red thing? Sorry, it's kind of hard, really hard to see. Here's my inverted graph. Is the red inverted graph, is that a function? Look at, I can take my ruler, I can try and draw a line through it. Look at, I passed through 2 red sections. So, note, in this case, in this example, the inverse is not a function. It fails the vertical line test. And just to finish this out, let's talk about the domain and range of the original function, which was what? From negative 2 to positive 5, right? And what was the range from from 1 to 6, agreed? It's kind of hard to see. This was my original, right? 1 to 6, yeah. Okay, so the domain and range, okay, by the way, this is wrong. You have to scratch this out. It's not, we just have to call it the inverse. It's not it's not an f function because it's not, I can't use that symbol because it's not a function. What is, now I'm just looking at the red graph. The range is from negative 2 to positive 5. And the domain is from positive 1 to positive 6. Okay. So hopefully you weren't surprised at that. How do the domain and range of the original compare to the domain and range of the inverse? How do these two compare to these two? They're just switched, right? Which makes sense. If you switch the x and the y values, the domain and range are going to switch. Okay? I'm wondering if I should just... Okay, I'm going to do example 2. I'm going to skip 3 and 4 because they're pretty much the same, and you could do them on your own if you want. And then we're going to do some algebra. So I'll do 2 and 3, then I'll get you guys to go for a break. And then we'll finish up and I'll tell you what your homework can be. All right, determine the equation of the inverse of each function. Sketch graphs f of x and its inverse. All right, this is one of your parent functions. What type of function is this? What do I call this type of equation? Linear? Thanks, Johannes. Was that you too, Evie? That's a linear function. What about this guy? Okay, does everyone know how to graph this guy quick? Who wants to help me out? How would you graph this guy quick without using table of values? What do these numbers mean? What does the half mean? What does the 1 mean? Y-intercept is 1, right? Because it's in mx plus b, and the slope is 1 over 2. Agreed? So we shouldn't have to make a table of values. My y-intercept is 1. Then from that point, I rise up 1 over 2. And I can keep that pattern going for a couple of points if I want. Up 1 over 2, up 1 over 2. I could kind of even work backwards if I wanted to. You only need 2 points to draw a line, but I like drawing a little more. And all the way across the page when you draw your line. Okay, so there's my y equals half x plus 1. That's the quickest way. Okay? So I graphed 4 points because that's actually going to help me draw my inverse. Now they want me to draw an inverse of each function. I think sometimes it helps to actually have your y equals x line drawn in. So let's draw that in too. Let's draw our y equals x line so we know what we're... So I'm just drawing a diagonal through the quadrant, right through the points 1, 1, 2, 2, 3, 3. Right, you're drawing a perfect diagonal through quadrant 1 and 3. We usually draw it like this. So here's my y equals x line. All right, so now I'm going to draw the inverse, sketch the inverse, and maybe I'll try it in a different color too so it shows up a bit better. If I can find a blue pen. Probably only black. Abdullah, can I borrow your blue pen? I'm going to draw. Thanks. Okay, so can we do it without making a critical table of values? Let's try. What is this point? What are the coordinates of this point? 0, 1. So I'm going to have a point of 1, 0. This point, 2, 2. That's going to remain on my inverse graph, right? Because if I switch the 2 and the 2, it still stays 2, 2. Okay. This point, x is 4, y is 3. Let's switch that. 3, 4. All right, last point, I've got 6, 4, so it becomes 4, 6. All right, I connect the blue. Is the inverse, so here's my original, here's my inverse. That's what two linears look as mirror images of each other over that line. So hopefully you can see any point that lies on the y equals x line will remain on both graphs, right? Is the blue graph itself a function? Is the inverse a function this time? Yes. It is, yeah. So I would say that this is, if that's f of x, then I could call this y equals, I can use the special symbol for it. Now, if I wanted to, I guess I could come up with an equation for it. This is kind of interesting because it's a pretty easy equation. Could you guys figure out what the equation of this is? Of the linear is? From your knowledge, the equation of y equals f minus 1x, like the actual equation. Well, let's see. We've got y-intercept of 2, right? Y-intercept is negative 2. What's the slope? Up 2 over 1. Slope is 2. Okay? So putting that in y equals form. Was that you, Adam? Yeah. So f minus 1x would be equal to what? 2x minus 2. Just to refresh and review old skills, right? I didn't ask it, the example didn't ask that, but we could easily come up with that, right? Okay, for the next one, Then I'm going to send you on a break. Let's sketch in our y equals x line first. So perfect diagonal through both quadrants 1 and 3. Y equals x. Okay. Can you sketch that one quickly for me? What do I know about this quadratic? I have to know the vertex, right? And it's kind of nice to know the next two lines maybe. What's the vertex of this quadratic? 2, 5. And then it has a regular climb, right? Like the a value, a is 1, so that kind of tells me where my first couple of sets of points are, or I hope it does. So I have 2, 5. This one's going to be hard to draw because they didn't give me a big enough grid, right? It opens up, agreed? So my next point is just going to be 1 up, 1 over, 1 up, 1 over. Then it would be 2 over 4 up, right? Something like that. But I'm off the grid. So the best I can do is this. Okay, that's my original. Can you picture in your head what the inverse will look like? If this guy is reflected over this line, can you picture what it looks like? What will it look like? Will it be flipped down? Yeah? Yeah, it's not going to be flipped down, because if it was flipped down, it would be reflective of x, so it's not flipped down. It's going to be a rotation, like a 90-degree rotation, right? Okay, so let's see, what's the quickest way to graph the inverse? I'm just asking you to draw the picture. What's the quickest way? If I told you to draw the inverse right now, what would you do? Yeah, so I got 3 points identified, right? Let's just do those quick. So what would this point be? 1, 6. So I have a 6, 1. Okay. 2, 5. So that means I must have a 5, 2. And finally 3, 6. So I must have a 6, 3. Okay, so you're right, Adam. I connect these dots, right? It's too bad we ran out of room so we could have another. And sideways parabola. Okay, this was my quadratic function. This is my inverse. Is the inverse itself a function? The inverse is not a function. Now, if I told you to come up with the equation of this one, I think it would be hard because you haven't studied sideways parabolas, right? This one you should be able to give me the equation of any line, because you guys know lines, but you've never studied a sideways parabola. So I'm going to, after the break, I'm going to show you how to come up with the equation of the inverse without even knowing what a sideways parabola looks like, right? This might have been your first exposure. So there's an easy way to come up with the equation of any function. There's an easier way, maybe, I don't know, you might not think it's easier, but I can show you another way to come up with the equation of this guy too, if you kind of forgot about your graphing skills. And I'll do that after the break. So we'll take a break, maybe between 5 and 10 after. I'm going to skip over example 2 and 3, just because I think you guys are getting this. And then we'll finish up example 5, and I'll tell you what you can work on the long weekend.